Good morning, everyone. We get ready for this sixth webinar going over dissipation. I'm excited about it. Love to learn more about it. Gerald, I'd like to turn it over to you.
Thanks, Troy, and welcome everybody. As Troy was already saying, if you have any questions about CPT, please let us know. And that is really the reason why today we're talking about the dissipation tests some more. A couple of webinars ago, we talked about the pore pressure and how you measure that with the CPT. And there were quite a few questions, follow-up questions about dissipation test, and give us some more details and some of the practical problems that people are encountering when they do a dissipation test. So that's why we're going to talk about it today. What is really the program that we have in mind for today is we start off with some fundamental questions to cover this topic, talk about hydrostatic pressure, CPT, pore pressure, etc. Then we talk about what the dissipation test is and how you can really use it, whether it's to determine the water table or to determine hydraulic conductivity. And then, as I mentioned earlier, talk about some practical issues associated with dissipation tests. Sometimes things just don't happen the way you expect them, and then it's nice if you have at least in the back of your mind what to do then and how to address it, and then finally come up with a conclusion. What I'm not trying to do is overload you with a whole bunch of equations and why the dissipation test works the way it does. Peter Robertson gave a presentation on a webinar about 7 years ago or so, in which he went to much more the details and the theory behind the dissipation test. And if you're interested in it, I'm more than happy to give you a link to that. I would just want to give it a more practical slant in this webinar to tell you what it is, what you can do, and also how you can avoid some problems. Let's start with some very fundamental questions. And one of the things that we need to talk about is the hydrostatic pressure, which is basically the pressure that you experienced or that the fluid experiences when it's in equilibrium. And that's very important. And we're not talking about the fluid that is moving, but it's purely at equilibrium at a given point within that fluid, and it's all caused because of the gravity. And what you see here on the right-hand side is a CPT profile, tip resistance only. The brown line at the top indicates the grade level, and you see the solid blue line, which is where the water table is. In this case, about 7 meters below grade. The units really don't make any difference here. And then you see that with the dashed blue line is how slowly the hydrostatic pressure increases. Yeah, all as a function of gravity. And just to give you an idea how quickly that hydrostatic pressure increases, it's about 0.1 bar per meter. Every 10 meters or so, it will go up by a bar. But if you're more used to inch pound units, it goes up by about 0.43 psi per foot. And that's something that I would definitely keep in mind, that number, whatever units you're normally working in, so that you have a feel in the field whether things are really happening the way they should be happening. Second thing that we need to talk about is what is CPT. And then for those of you that have been watching these webinars, you may sometimes feel that I keep coming back to the same thing time and time again. And I do that to really show you different angles to get you familiar with different aspects of CPT and then how they affect the results that you're getting. You've seen the picture on the left-hand side, a cone truck, which is pushing a cone into to the ground. And what we're going to talk about today, of course, is again pore water pressure, because the hydrostatic pressure or the pore water pressure, you measure that with the cone, with a piece of cone. And what is important in this case is that when we talk about CPT, that we are using a cone that is pushed into the ground at a continuous rate. That means that the cone is not at rest. The cone keeps going down and down and down. And as the cone goes down, it pushes the soil to the side because the cone has to penetrate the soil more and more. And that means that near the cone tip, the situation is not static. And that is what is important here when you say, what is now the measured pore pressure? It cannot be the hydrostatic pressure because, as I said earlier, the hydrostatic pressure is when the situation is static, when it's not moving. But that cone is moving through the soil, and therefore the measured pore pressure simply cannot be the hydrostatic pressure. And you see that again in the same figure on the right-hand side, or the left-hand side that I showed you earlier. The dashed blue line is the hydrostatic pressure, how it slowly increases. The black line is the pore pressure that is measured in the cone, and you see that below the water table there is a huge difference. And the reason that there is a difference is because what we measure in the cone is the dynamic pore pressure. It is the pore pressure that is affected by the hydrostatic pressure, obviously, but also by the dynamic effects as the cone moves into the soil. And that's why it is the dynamic pore pressure. Now, when we look some more at this dynamic pore pressure, and again, it's a figure that I've shown you before, what you see on the left-hand side is a graph where on the horizontal axis, we are showing the ratio between the measured pore pressure, or the dynamic pore pressure, if you wish, over the hydrostatic pressure, U0. And you see there we go from 0 to about 25. On the vertical axis, where the 0 is at the origin, we have the cone tip, and then we slowly go up backwards, first to the U1 position, which is about halfway through the cone tip, then go to the shoulder of the cone tip, the U2 position, where we normally measure the pore pressure, and then finally go to the U3 position, which is behind the friction sleeve. Today, we're only going to talk about U2, but what you see is the tremendous range for different types of soils where you have that U2 pressure. Over here in this Taranto clay, the U2 pressure is about 15 times the hydrostatic pressure. So what is fair to say is that depending on the soil type, that U2 pore pressure, the dynamic pore pressure reading, can be much higher than the hydrostatic pressure. But if you go to different soils, it can also be less, or even over here, it's going to be less than the pore pressure, and even it can be slightly negative. So you have a huge range of the measured pore pressure, the dynamic pore pressure, as a function of the hydrostatic pressure. And that is very important to keep in mind. Now, finally, what do we do with these pore pressure readings? And one of the ways that we can use them is to come up with a soil classification. And you see here the Robertson and Campanella classification, the soil behavior types. On the left-hand side, the relation as a function of the tip resistance on the vertical axis and the friction ratio on the horizontal axis. But what I want to focus on today is the one on the right-hand side, where again on the vertical axis we show the tip resistance QT, and on the horizontal pressure, a pore pressure parameter, which is basically a function of the measured pore water pressure U2 minus U0. So it's kind of the difference, the excess pore water pressure, if you wish, the difference between the measured and the hydrostatic pressure. A couple of things that are important here is, first, what you see here, this is the 0 value. You see again that there's quite a bit of options, quite a few options here where you have a negative pore pressure parameter, because U2 can be less than U0, U0, and therefore it is very well recognized that you can have a negative pore pressure reading as you go down. So what does it what do you do with it in the field? What you see here is from a test that we have done. You see the soil characterization and soil behavior types. It's not relevant right now what those colors mean, but you see on the first column the soil behavior type as a function based on the tip resistance and the sleeve friction. And then the second one is a function of the tip resistance and this BQ, or this the pore water pressure parameter. And you see that those two don't necessarily always completely agree, and that's quite often people take an average to get an idea of what kind of soil we have. But in order to do this, in order to have these BQ, as I said earlier, we need to know the hydrostatic pressure, because what we're using in BQ is the excess pore pressure, the difference between the measured pore pressure, the U2 pressure, or the dynamic pore pressure, and the hydrostatic pressure. So we need to know where the groundwater table is, because if we don't know where the groundwater table is, we don't know what the hydrostatic pressure is. One way of achieving that is by doing a dissipation test. Now, what a dissipation test really is we just stop penetrating the cone, we unload the push rods, and we keep recording the pore water pressure as a function of time. And what you see here on the left-hand side, the green line, is basically the result of that. We started out somewhere around 0.395 megapascal, and again, forget about the units. And we just kept going, and after a while it was 300, and then it went to 200 and 150, and we kept going, waiting, and finally it stabilized somewhere around 0.035 megapascal. And with that, we then can calculate what the equilibrium pore water pressure is at a 0.035 megapascal. Based on the numbers that I gave you before, you can then calculate that the water table is about 3.57 meters above where this test is done. And if you're more familiar with inch-pound units, the 0.035 megapascal is about 5.08 psi. If you divide it by 0.433, then you know that the water table is about 11.73 feet above where the test is done. So with that, we can now figure out where the water table was. We know at which depth we are. We can calculate if we wait just long enough and we see that water pressure has stabilized. We wait long enough, then we can figure out where this water table is. But there's something else that's important when you look at this chart, and that is the horizontal axis. As you see there, it's a log scale. From here to there is 10, and then the same distance goes to 100, and the same distance goes to 1,000, etc. in seconds this time. And that gives a very misleading picture, of course, of this whole thing. Because what you see here is that when you see a log scale for time, it generally means that things can last a long time, because you want to really capture all the information in one graph. And that is true. If you are in cohesive soils or even in plastic clays, it can take several days before you finally reach its equilibrium pressure. Now, in this case, where we did this test, it was not that bad. We see that we reached the equilibrium pressure after about 330 seconds, a little over 5 minutes. But what you can also see is that the first 50%, because this T50 basically means when 50% of the excess pressure has dissipated, the first 50% was dissipated in about 8 seconds. The final 50% in about 320 seconds, or 40 times longer. So it basically means that this test, it lasts long, but the first part goes relatively fast, a lot faster than the second part, which is not a surprise, but then because you don't have more driving force to push the water out of the soil. And that was the reason why people said, now, okay, if I already know where my groundwater level is, so if I already know or can calculate what my equilibrium pore water pressure is, then let's just do this test, but only go dissipate the first 50%. Because that goes relatively fast, a lot faster than the last part, factor 40 or something like that. So let's just go and characterize this dissipation test based on dissipating only half of the excess pore water pressure. And the reason that they do that is in this graph that I've shown you before as well, because the T50 gives a very good indication of what type of soil you have. but also a very good indication of the magnitude of the hydraulic conductivity. Now, when you see, for instance, when you have a hydrostatic pressure or T50, sorry, of 10 seconds, then you see that you are most likely in silty sand or sandy silt, and you have a hydraulic conductivity somewhere of about 1 to the 10 power minus 4 to minus 5 in that order of magnitude. But you can see that the range for the hydraulic conductivity as a function of for a specific T50 is relatively small. It's a really narrative graph. And that means that this T50 is a very good way to develop or to determine the hydraulic conductivity. Provided, and I showed this box a little bit too soon, but it's important, provided the test conditions are constant. Now, when you do this test, you cannot change the test conditions. And that means that before we start the test, we make sure that we unclamp the cone and the rods so that we let just the cone sit in the soil. We're not pushing it farther down or keep it under stress. We just let it sit there, and that way we can do the test. So that's kind of what the dissipation test is all about. Now, relatively straightforward. Now you just sit there and wait. And that brings me then immediately to the practical issue. The first one is it could take quite a bit of time. And if you're in a hurry and you do your dissipation test in certain soils, it is sometimes a big problem. Now, when you want to determine the water table, you better do it in sand, because as I showed you earlier, sand is your friend. And what do I mean by that? Is going back to this one, you see that sand, you have a T50 of about 1 second, 10 seconds, 30 seconds, something like that, but relatively short. If you try to figure out where your hydrostatic, the water table is, by doing a dissipation test in clay, your T50 could be 3,000 seconds, 4,000 seconds, 5,000 seconds, so well over an hour. And that's only the T50. If you want to wait all the way until you get your hydrostatic pressure, you are talking about many hours, sometimes several days. So that is why if you don't know where your water table is, do it in sand. The T50 is relatively short, and that means that your final pressure will equalize relatively quick in a matter of minutes rather than hours or days. But sometimes you have to find the K value, and people will say, okay, you have to do your, where your hydrostatic, the water table is, so you know your hydrostatic pressure. You now need to find out what the K value is. And if that happens to be in clay, just be patient. Now, it can take a long time. And that's why in Holland we always say it's time for a cup of coffee or time for lunch. You can sit there for quite some time and just let it take its time. There's no way you can make it go faster. It just, the soil will take the time it takes to get to this new pressure level. Now, there's also another situation. Sometimes it is going so fast that by the time you unload the rods, the test is already over before it begins. It's kind of a roller coaster. Because again, going back to the graph that I showed you before, if you go to in sand, the T50 could be in seconds or even less than that, or a few seconds. So if you stop your test and you unclamp your rods, you may already be at the end of the test, and the roller coaster may have already brought you all the way down, not just to T50, but to the final equilibrium pressure. In that case, don't panic. Just do the test again, a little deeper, hopefully still in the same layer, but then without clamping. And just make a note in the report that this dissipation test was done without unclamping. You have a second chance. Bigger problem is situation that you see here. On the left-hand side, you see the horizontal axis again is in the log scale. Person did exactly what I just been talking about. It recorded, or he or she recorded the hydrostatic pressure in the cone. This is the blue line. Only problem was we started out with a negative value. Well, that was no problem. Negative value was remembered. At the beginning, Gerald talked about negative pore pressure, so that's okay. We'll just go sit and see what happens. And then you see that the negative value becomes less and less negative, and in the end goes positive at about 5 psi in this case. And that's where you see that peak there, over here, and then it goes slowly back down again. Question is, what peak do I use? What do I assume if I have to do just a T50 test, a normal dissipation test? What was my initial pore pressure? So when do I know that I have dissipated 50% of the excess pore pressure? The answer that I have to people like that is, again, don't panic, take your time, wait until you get the peak here, and then start recording about once a minute what the pore pressure is, and then call the office. Call the engineer that is in charge of this whole thing, because that engineer has some additional tools. When you do a pore pressure or dissipation test, the horizontal, there's a part of the curve where if you don't use a log scale for your time, but a root scale of your time, and again, what you see here at the peak was somewhere around 400 seconds, and that's the square root of 400 is about 20 seconds. So there at the peak, what you can do is if you plot your hydrostatic pressures with a root time scale, then for a while you're going to get a linear graph, and you can extrapolate that to 0 point, and that's where you're going to get there you assumed initial pore pressure. So we see that we have assumed an initial pore pressure of about 10.5, and that basically means that 50% brings you down to a little over 5, and that means that the T50 is somewhere around slightly less than 400 seconds. Now, why do I say that you, if you are in the field, you start recording that about once a minute? It's simply, you could already have dissipated, just like in this case, and that peak takes place after the T50. So the sooner the engineers are looking at this whole thing, the better it is. But again, don't panic. Just record what you have and let the engineers figure out what needs to happen. So with that, I'm at the end of this presentation, and we always try to keep these presentations within about half an hour. The conclusion is very simple. Dissipation test is a very useful test. You can determine the groundwater level with it. Now, ideally speaking, do the test then when you're in sand, or you can determine the soil conductivity, and it gives you the T50 gives you a fairly accurate idea of what this soil conductivity is, which then helps you to develop settlement calculations or do other engineering work with that. Sometimes the test generates unexpected results. But, and that's very important to remember, with some common sense, if it goes too fast, just do it again, a little deeper, don't unclamp, or let the pressure come from negative, go back to positive, and then when you see it dropping, record it for a few minutes, and then call the engineer to figure out whether or not you can already finish your test. And that's how it can generate very useful information.
Yeah, thanks, Gerald. I appreciate your time on that. We had 2 people responses. One was, is it possible to have a certificate for the webinar?
We can issue a certificate to this webinar. These webinars don't necessarily qualify you for PDHs. simply because we haven't necessarily obtained permission to do that. Maybe that's something we can do in the future. But we can definitely, if you're interested for your within your company to have some record that you attended this webinar, send an email to us, and we'll get you a certificate out that you attended this thing.
Excellent, that'd help out. I just had a question come in as well, is could you provide insights how to accurately calculate the groundwater level from the dissipation data?
Yeah, that is no problem. That is, I think, what you saw here. And let's just assume that the gentleman is asking it in inch-pound units or in SI units. But basically, what you do is you stop your CPT. You at that time measure what your pore water pressure is that you measure, your U2 pressure, which is your dynamic pore pressure. You then sit and wait until you see no longer a drop in hydrostatic pressure. That gets you your final pressure, equilibrium pore pressure. And then based on that, with the parameters that I showed you at the very beginning, I'm going to go all the way, where are we? Here. The difference between the initial pressure and the final pressure, the difference, if you divide it by the numbers that you see now at the bottom of your screen, then you know how many meters or how many feet the water table is above the depth where you do the test. And it's a very accurate test. No big problems with that, except that if you do it in clay, it can take a long time. So generally speaking, what I suggest people that they do is to do, if they don't know the hydrostatic pressure, because in order to analyze your CPT data, as I showed you earlier, you need that water table, is do your CPT. When you see a friction ratio that is 1% or less, then you know that you're in sand, and then pick a level there where you think now below the hydrostatic pressure, or below the water table, and then just do the dissipation test, and that way and you can determine how much higher above where you are at that time the water table is. Any other questions?
Yeah, we are. Thanks for that. In some soils with high shell fragments content, we have had dynamic pore pressure in clay soil. A way for us to confirm that the cone is responding well was by performing dissipation test. Then pore pressure would build up and start to dissipate. My question is, how valid would be the dissipation test?
Well, when the pore pressure, and again, that sometimes happens. I showed you an example where we started out with a negative pressure, but you can also do this, the same thing that you can see in the positive pressure. Don't worry, just let the pore pressure increase. Then once you have seen the maximum level, record the pore pressure, not only in the graph on a continuous basis, but every other minute or so. Call the office back, because they can do exactly the same thing that I showed you here with a root time horizontal axis to figure out what the assumed initial pore pressure is, and then figure out what your T50 is, and that's still a very accurate assessment of your T50.
Okay. One of the questions, the last one that just came in, thought to clarify that the test was completed offshore in 4-meter water depth.
Okay, well, what we can do is I will look at that question after this webinar, because we already passed the bottom of the hour.
Excellent, thanks, Gerald. I got one last question. If you could tell us, there's one question, 5.08 over 0.433. What is that 0.433 number? What does that refer to?
The 0.433 number is the increase in the hydrostatic pressure per foot. Yeah, what you see here, if you calculate and I'll go back there, if you look at the hydrostatic pressure, how it increases by 0.1 bar per meter. That you see here as well. And then on the 4 inch-pound units, it also increases by 0.433 psi per foot. So if you calculate the excess pore water pressure, which is the difference between the measured pore water pressure and the hydrostatic pressure, and you divide it by 0.433, then you get psi divided by psi over foot. So that gets you a distance in feet. That gives you how much higher the water table is above the level where you are doing the test.
Thanks, Gerald.